In this video, we are going to compare and contrast various algorithms used to solve the problem known as kmin.
The kmin problem states that given a set of n numbers, how can we find the k smallest number? We will look at three various algorithms to solve this. Our algorithms include implementations of our own binary search tree and a heap, and C's implementation of quicksort. The first algorithm we use is quicksort. To find kmin, we use C's built-in quicksort to order all of the numbers in an array. After the numbers are ordered, we know that the kth smallest number will be at index k-1. The worst case time complexity of this function is n squared, with an average case of n log n.
The next algorithm involves using a heap. For this solution, we heapify all of our elements within an array. Next, we extract the min value and reheapify it. We perform this extraction and run this algorithm k times. This kth extraction will be our kmin value. Since building the heap takes linear time and extracting and reheapifying the heap k times takes log n each time, our worst case time for this algorithm is big O n plus k log n.
Our final algorithm uses our binary search tree to find kmin. In order to do this, we load all of our values into a binary search tree. Next, we find the minimum value of the tree and call successor on it. We continue to call the successor function on the return value of each call k-1 times. The final successor call gives us the k smallest number. Since our binary search tree stores duplicate values by holding a count of variables at each node, we can skip any unnecessary predecessor calls by keeping track of where we are in the numbers. We do this through checking the count of duplicates which are returned from the predecessor call. If the position plus the number of duplicates includes our k value, then we can return the number from the predecessor call. If our k value is larger, then we continue to call predecessor until we find it. Building our binary search tree takes big O n log n worst case time. Finding the minimum takes big O n worst case time, and calling successor a max of k times takes big O k log n. This gives us a total time of big O n log n plus k log n plus n, which we can simplify down to big O of n log n.
To test all of our algorithms, we generated three separate files of 1 million random numbers, one for each trial. We then ran all three algorithms on a set of data 3 times for various k values and averaged the results. We then repeated this process on the other two sets of numbers to further confirm our results.
As you can see, the graphs of the average of 3 runs appear to be consistent with each other, with the heap being the fastest of the 3 algorithms up to the 250,000th number and the slowest past the 500,000th number. Since the quicksort algorithm spends the majority of its time sorting the data, and the data is the same for every iteration of k, this is why we see a fairly consistent time across various k's for that algorithm. Binary search tree is similar in that the algorithm spends most of its time during the insertion of the values into the tree. While making all the successor calls could potentially cause us to see spikes in time as k grows, we get around this by throwing out duplicates if our k is not in that range. Having duplicates in the data effectively reduced the number of successor calls we needed to make by a factor of 1 over the average number of duplicates. Because the time spent making successor calls was reduced, most of our time is dependent on building the tree. This is why we see a similarly consistent time across all k values for the binary search tree. If we allowed less duplicates in our data, we would expect to see this time of binary search tree to rise as k rises. The time heap spends on sorting, on the other hand, is greatly affected by the varying k values because it has no way of skipping redundant data and must instead perform k extractions. That is why we see an increase in the time spent as our k value grows.
We can conclude our analysis by saying that in cases where we will be searching for k of 250,000 or less, the heap algorithm was the most optimal choice. When searching for k values of 250,000 or more, quicksort performed the best. This is because the time it took to sort all of the numbers and extract the kmin in constant time outperformed the time it took to build the 2 other structures and perform the various methods of extraction. In data where duplicates are expected, the binary search tree performs fairly consistent for varying k values. Whereas in cases where duplicates are not present, we would expect the binary search tree algorithm to perform slower as k grows, similar to the heap algorithm.